In this module, I will talk about the different methods on how to sort an array on whether you want them in ascending or descending order, and then how to efficiently search for a specific element in an array. I shall do this by implementing two different searching algorithms, the linear search and binary search, and then the two different sorting algorithms, the bubble sort and the selection sort. As I discuss each algorithm, I will also explain what they are, how they work, and the conditions in which it is best to use them. The linear search algorithm loops through each element in an array searching for a value. It starts at the first element and compares each element until the value is found or the end of the array has been reached. And if the value has been found, it returns its position in the array. The advantages of this algorithm are that it is simple to understand, easy to implement, and that elements don't have to be in any particular order. Its disadvantages are that it has to search through each element. Because of this, it's slow and inefficient for large arrays. Let's run through this program. On lines 7 through 10, we prepare the variables that we'll use to test this algorithm, not the algorithm itself. We declare an array with some values and a variable called item ID that will hold the number that we'll be looking for in the array. The lines 12 through 30 hold the actual code for the linear search. Then we create a variable to hold the index of the array as we search through it. We then make a variable that will hold the position of the found variable. We assign it the value of -1 to let us know that the searched variable was not found. If this algorithm was in a function that returned the index, it would let us know that the element was not found, since an array cannot have a negative index. We also have a Boolean variable that serves a similar purpose. Here inside a while loop, we start iterating through all the elements of an array, one by one, until either the number has been found or it has searched through all the elements of the array. If found, the found variable is set to true and the index variable gets the index of where the number was found. After the loop ends, the results are printed out. In our example, we searched for the number 823, which was found to be in the fourth position of our array. The program then outputs 3, which is the index of the value. The binary search algorithm is a fast way of searching for a value by eliminating half the elements every time the search fails, with the requirements of the elements having to be in order. Basically, it starts at the middle, and if that value is greater, then it discards all the elements from that point on and goes to the middle of the remaining elements to do the same till the value is found or all possible elements have been checked. The advantage of this algorithm are that it is quick and efficient, and that each fail attempt cuts the remaining in half. Its only disadvantage is that the elements in the array must be in order. In this example, we have a program similar to the linear search algorithm. Here, though, we declare three variables: first, last, and middle. First and last hold the position of the current half that is to be searched. The variable middle holds the middle point between first and last. This index will be the one used to get and compare the elements of the array with the desired value. In this case, if the element of the index in middle is larger than the value in the variable num, then the value has to be found on the upper half. The value of last is set to be the one of middle, and the variable first is untouched. If the element of the index in middle is lower than value in the variable num, then the value has to be found on the lower half. The value of first is set to be the one of middle, and the variable last is untouched. The loop ends when either the value is found or the values for first and last are the same, which implies that the element is not contained in the array. If the values of the array and the desired number match, then the Boolean flag is set to true and the value of middle is assigned to position. The program prints on the console the results when it is done. In our example, we search in our array for the number 18. The program then starts to iterate through the array to find it, printing the results at the end of each loop. After 3 iterations, it finds the value and prints 18 as the position of the value in the array. The bubble sort is a sorting algorithm that arranges data in ascending or descending order. If we were to place them in ascending order, the bubble sort would start comparing the first element with the second. If the first one is larger than the second, then they trade places. If not, then it moves to the second element and compares it with the third. If the second is larger, then it trades places with the third. Then it moves to compare the third with the fourth, and so forth, till it reaches the end of the array, and it starts over the process and continues till it can loop through the entire array without making a single change. From lines 10 to 31 is our bubble sort. First, we declare two variables, swap and temp. The bubble sort needs to loop until all the elements in the array are in order. Variable swap serves as a flag that if at the end of the loop there are no swaps, the array is in order and the sorting terminates. The loop starts by setting swap to false. If the array is already in order, the program terminates. The program then starts searching through the elements of the array and comparing the elements of the current index with the following one. If the following number is smaller, they are swapped. The current value is stored in temp, overwritten by the element of lower value, and then that element is overwritten by the value inside temp. Since a swap has been made, swap has been set to true. The program needs to loop one more time to ensure that the array is in order. Once this is done, the program ends. On line 28, we make use of a small function that simply prints the array. This is used at the end of every iteration to be able to see the results of the sorting on the console. Here is a visual representation of the first couple of loops. On the first loop, the first two elements are swapped. On the next loop, the numbers 2 and 4 are swapped. On the following one, since 4 is smaller than 5, they are not changed, and the program moves to compare the next pair of elements. Here, 5 is swapped with the number 1. The program continues to loop until the array is in order. The final result can be seen on the program's output. The selection sort is an algorithm for arranging values in an array in either ascending or descending order. If the values are to be ordered in ascending order, then the loop will be scanned for the lowest value and placed first. Then it'll scan for the second lowest and place it second, and it'll continue till the end of the array. Generally speaking, the selection sort is more efficient than the bubble sort when arranging large arrays because it directly moves a value to its correct position and will only do one loop less than the array size, where the bubble sort only moves a value by one element at a time. The implementation of this is found on lines 10 through 28. What is done is that we use a variable to hold the index of where the smallest value is to be placed once found. In our program, we called it position. We also make another variable to hold the lowest value called value. The program searches through the array, finding the smallest number and storing it in value. When it finds a smaller number than the one value currently holding, it stores that value inside the variable along with its index inside position. When it is done searching through the array, the inner loop ends. The outer loop swaps the values of the starting element with the element that holds the smallest number. This sorting algorithm goes in order, putting the elements in their place, so it does not need to go back through the elements that it has already sorted. The program does this by incrementing the starting point of the search at the end of each iteration. This is done by using the variable start as the counter variable of the outer loop and using it again to set the counter variable for the outer loop. The program ends when the array has been placed in order. Just like in the previous slide, we have also included a function to print the array to be able to see the results of the sort. Here is a visual representation. The program finds the smallest number and places it on its proper position. On the first loop, it finds the number 2 and places it on the first position of the array, swapping it with 3. Now you'll see on the left of the arrays the three variables start, value, and position. The variable start is going to hold the position that the outer loop is in. The variable value will hold the smallest value found, and the variable position will hold the position in which it was found. And in the array, the arrow represents the starting point for the inner for loop. On the second try, since 3 is already in its proper position, it does not replace it. The next time, it replaces 8 with 6. And in the next loop, it does nothing since the array is already in proper position. and then we finish with our sorted array. This can be seen on the program's output.